All right, this is going to be one of a couple videos probably that will walk us through a simulation where we're going to have a 3D geometry and we're going to vary some of the properties within that geometry. And so just for context of what we'll eventually be looking at, we're going to be simulating flow past a wedge. And so we'll talk a little bit more about the motivation in class for this particular project. But we're going to have this triangular wedge where we have flow coming in from the left, going over the tip, and then passing out to the right. We're going to have to create a three-dimensional mesh. And in fact, in our case, we're going to assume that the wedge is stationary despite the flow moving around it. And then ultimately, we're going to be calculating a steady state drag force. And so this is our velocity field. So you can see we have relatively constant velocities, and then we have our no-slip boundary condition around our wedge, a very stagnant region or wake behind the wedge, and then flow leaving out the right word. And so what we want to do is we want to vary the angle of the wedge and evaluate how that variation of the angle impacts the drag coefficient and the drag force on the object itself. So this first video is going to focus on developing the geometry, that three-dimensional geometry, as well as the mesh that we'll be using to solve. The second video will be provided that will walk through the setup and then the parameter variation. All right, let's get started. So we're starting with a clean workbench. We're going to go ahead and use Fluent for our geometry. We're going to keep our analysis as three-dimensional, so nothing's going to change here. And we're going to go ahead and open up our design model. So the first thing we're going to do is we're going to create our diffusion fish itself. And we'll talk a little bit about what the diffusion fish is in class. But we're going to set the horizontal length scale of the fish to be 10 centimeters. So from tip to back will be 10 centimeters. And then the angle from the x-axis to the top slope will be 10 degrees. And then the bottom slope will be symmetric across the x-axis. We're going to create an extrude of that shape of about 2.5 centimeters in each direction, so for a total of 5 centimeter wide fish. Okay, let's go ahead and get started. So we want to pop in our XY axis. Let's take a look at that. We'll orient ourselves so that we're normal to that axis. Go into sketching. Actually, before we do that, we're going to change our units down to centimeters, so this gets a little bit closer to the length scale that we're interested in. So again, we're going to create a line, which is a horizontal length going from the origin, sloping backwards. We'll have a horizontal length of 10 centimeters. We'll get to the dimensions in a moment. We'll just go ahead and create our wedge or triangle with the tip on the origin. So not exactly symmetric. At this point, all of our lines are light teal, which means we need to go ahead and start defining some of our dimensions to properly constrain the object. So the first dimension we're going to do is a horizontal distance from the tip to the back of the wedge. And that distance we said will be 10 centimeters. Okay. Now we're going to use an angle calculation, an angle measure from our x-axis up to the top of our slope. And that's going to be a 10-degree angle. Okay. And this is where we're going to set our parameter that we're going to allow to vary. So we're going to allow our slope angle to vary from 10 degrees, maybe down to 5 degrees, up to 20 or 30 degrees, and see how that impacts the slope. So to allow us to create a parameter, we're going to click on this open box next to A2. So it's going to create a parameter name, and we're going to just call this slope angle. Okay, so you'll see a little P pops up next to A2 or whatever your variable name is. Okay. All right, the last thing we need to do, we still have one teal line down here. We're going to set a constraint. And so a constraint, similar to like what you would have in SolidWorks, sets constraints on, or sets relationships instead of necessarily having to set a dimension for each one. And so we're going to use the constraint that we're going to require two of our sides to have equal length. And so as long as both slopes have equal length, we know that it'll be symmetric across the x-axis. So that completes our sketch for our diffusion fish. So this is what our triangle looks like. And now we're going to go back into modeling. We're going to highlight sketch 1, and we're going to do create extrude. So extrude, similar to SolidWorks, is going to create a body, basically a prism, with whatever the base is based on your sketch. And so in our case, we have a triangular prism. And what we want to do is, so we're fine with the geometry selection. We're going to go in the direction. The normal direction is fine. But the extend type, let's see. Oh, sorry, the direction itself. This is where we're going to set both symmetric, so we're going to extend in both directions. In this case, it's currently set to be 20 centimeters. It's obviously wider than what we want. We want to turn this down to about 2.5 centimeters. So the width of our wedge is about 5 centimeters total in width. Okay? One other thing that we're going to do, because eventually we're going to actually take this wedge and remove it from the rest of the fluid domain because we're just modeling the fluid. We're not necessarily interested in what's going on inside the wedge for this particular example. The operation that we're going to use is called add frozen. Okay? Generate this, and that generates our body, our first body that we're interested in. All right. So that created the fish. Now we need to create the water around the fish. So we're going to just go ahead and create a new sketch. So for XY plane, we're going to hit this sketch icon here with the little star at the top left corner. It says new sketch. So now we have sketch 2. We can go into sketching here. And we're going to just go ahead and create a rectangle around our wedge. And we're going to set some dimensions so that we can properly size it. So the dimensions, the top dimension, we're going to set to be 50 centimeters. Our total vertical dimension, we're going to set to be 30 centimeters. And then we're going to set the horizontal distance from the front to the tip as 20 centimeters. And we're going to set the vertical distance from the top or the bottom to the tip as 15 centimeters. And so we can go ahead and zoom out and see that we have the same amount of space above and below the wedge, and we have our incoming and outgoing geometry. Okay, so that creates our second sketch. We're going to go ahead and create another extrude. So in this case, we're going to have the extrude go in both directions again. In this case, the distance will be 15 centimeters. So this should actually create a 30 by 30 cube or square for our outlet and for inlet. Okay, we'll go ahead and generate this. So now one of the challenges that you're going to be facing as we go through the rest of the geometry part in the mesh is that sometimes we can't see the wedge. And so in cases where we want to see the wedge, we're going to have to hide some of our faces. So I'm going to go ahead and start doing an example of this. So I'm going to click on the top face, and I'm going to highlight each of the side faces. Right click, and we have the option here, hide faces. So that hides those 4 faces, and now I can see my wedge again. Okay, so right now, if we look into our drop-down, we see that we have 2 parts, 2 bodies. So body 1, that's our frozen, is our wedge. Body 2 is our fluid, or sort of the surrounding box. What we're going to do is we're going to create what's called a Boolean, which is going to take the wedge and subtract it from the body of fluid. What this is going to do is basically it's going to leave just the fluid part of the domain, which is what we're ultimately interested in modeling. So we're going to create Boolean. And the operation that we're going to do is we're going to subtract. Now there are a couple different options that you could use. You could use unite, where if you have maybe 2 different shapes that you want to merge together, that would be an example where you unite them. But in our case, we're actually removing part of the domain from the cube or the rectangular prism. So we're going to use the subtract function. So our target body, that's the body that we want to remove material from, is going to just be our larger cube. So our tool, that's going to be the material we're removing, or the shape that we're removing, is going to be our wedge. So you'll notice if I click somewhere on the body or in the domain, in the bottom left corner here, you'll see that there are a couple options. So the current option is highlighted in red, but we can go to a different layer or a layer below, which in our case we are wanting to do. So we can click on the next layer, which would be the wedge itself, and that would be the tool that we want to apply. Okay, we can go ahead and hit generate, and our Boolean has properly completed. Okay. All right, so how can we tell if we've actually been successful in doing this? Well, so we go back to our base cube or base rectangular prism. And now what we can do is we can do a slice or section view. So if we go to the top of our box, we can go click here on this sort of half filled in rectangle which says new section plane. And what you can do is you can just draw 2 points, and that will cut your geometry in half so we can see what's going on beneath. So then we can navigate around and see in here we've created our triangular cutout. So we've successfully created the cutout that we're looking for. Okay. And down here in our section plane, we can turn that off to go back to our cube face. Okay, so the last thing I want to do in this section is we're going to go ahead and create our name sections. So we're going to create an inlet at this end where the fluid is going to come in, move around the wedge, and then go through our outlet. We're going to have a free slip boundary condition on the sides of each of our rectangular prism that's not the inlet or outlet. And then on all 5 sides of our wedge, we're going to have a no slip boundary condition. So we can go ahead and click on our inlet face, right click, name selection. We only have one face, so that's fine. So this is going to be our inlet. Generate. Back here we have our outlet. Generate. Now we have our 4 sides. Which we will make sure we got all 4 sides, so that looks good. And this will be our free slip walls. Generate. And then we're going to select those 4 walls again. And we're going to go and hide those faces. So we can see our wedge in the interior, and we're going to select all 5 faces of the wedge. Okay, right click, name selection. This will be our no slip walls. It's important to make sure you got all 5 faces of the wedge, so we got it there. And then we can go ahead and generate. Okay, and that completes the geometry portion of our project. So we're going to go ahead and save our project. And you'll notice a little bit of a new feature from our normal workbench walkthrough, which is that we have this parameter set option that's going up to number 7 down here. And we'll circle back to this idea in the second video. Okay, so our project is saved, so we can close down our design modeler. And let's go ahead and open up our mesh. So we're not going to do too much to our mesh. We need to be very careful as we're generating the mesh that we don't have too many elements. So the more elements there are, the longer it's going to take for the simulation to work. And ultimately, there's a cap for the student version of your Ansys Fluent that you won't be able to have too high of a resolution effectively. So this is one of the challenges as you're thinking about the project, that you don't want to have too high of a resolution that your simulations take too long, or they simply won't run because of the version that we're operating on. Okay, so we have our cube. Let's go ahead and create our base mesh or default mesh. Really, we don't have a great view of what's going on, so let's go ahead and create one of those section views. So the icon is a little bit different, so section plane here, it's just a slightly different color. But we can cut through the middle, and then we can take a look inside to see, okay, here's our wedge. So if we're zooming in a little bit, you can see that we have very few cells, or the edges of a very few number of cells on our mesh, or on our wedge, which is a problem. That's the area where we're going to want to have our highest resolution. So what we're going to do is we're going to go ahead and go back, select all 5 faces of the wedge, and we're going to modify the base element size so we can have a higher resolution. Okay, so let's go ahead and zoom out, and we're going to turn our section plane off. And we're going to select our 4 edges again, and hopefully be able to go ahead and hide those faces. Okay. So we're not quite able to hide the faces, but I think we will be able to. So if you notice, it's very faint in the screen, but the outlines of the wedge faces is actually showing up despite the faces of the geometry or faces of the cube still being present. So what we're going to do is we're going to go ahead and try to highlight these 4 faces so you can see them a little bit better showing up in green. So that's our back panel. So now we got to get the bottom of our wedge. So our wedge is showing up in green, and so now we've got it on our right face as well. So for this, we're going to go back to mesh and go ahead and add a sizing. So for those 5 faces, we're going to set the default face size to be 2 millimeters. That's 0.002. Okay. So before we do that, let's take a look. So our base mesh, the statistics of that base mesh, were that we had about 8,700 elements. So this is the number you need to keep an eye on. This is the number of faces, number of volumes, number of nodes. And you want to keep this number low, but you need to have a sufficient amount of resolution. So this is sort of the balance you have to find as you're developing your mesh. So our target for this simulation is going to be about 180,000 elements. I think the code will allow you to get up to about 350,000 for the student version. Obviously, the more elements you have, the longer your run is going to take. So let's go ahead and update our mesh. Okay, so our face sizing has been implemented. Oh, maybe I've lost it. There we go. And now if we look at our mesh, our statistics show us that we have about 185,000 elements. So just by increasing the resolution just around the wedge, which it has only a 2 millimeter resolution, so it's not super small, but we can go ahead and get a better view of what that is going to look like if we go ahead and turn back on our section view. So now we can zoom in a little bit on our wedge, and we can see, okay, now the wedge is pretty clearly having more elements on the surface. So this is a higher resolution. We have an idea of roughly what the boundary layer thickness could be. Fortunately, we're going to be operating in relatively slow speed, so the boundary layer thickness is going to be pretty significant. Okay, so that's all we have for the mesh. The next video will walk us through the development of the model itself and then looking into how we can change the